Lighthouse Scientific Education presents a lecture in the Nuclear Chemistry series. The topic, Nuclear Chemistry, Part 2. Material in this lecture relies on an understanding of the previous lecture, Nuclear Chemistry, Part 1. There are two main topics in the Part 2 lecture. The first is fusion and fission, and the second one is half-life. Under that heading, we will be exploring carbon-14 dating and take a quiz to demonstrate problem solving. Prior to the main topics of the lecture, a brief review of the three main types of decay is given. Decay is an important concept in fission and half-life. Alpha particle decay is where a helium nucleus is emitted from a nucleus. It has a mass of 4 AMU and a nuclear charge of 2 from its 2 protons. It has a very weak capacity to penetrate matter, but is very dangerous because of its ability to form ions and free radicals. Beta decay is when a nucleus throws an electron. That's usually when a neutron splits into a proton and an electron. With essentially no mass and a charge of -1, it can penetrate a wood plank, and has about a tenth the ability of forming ions as the alpha particle. The third type of emission is in the form of a high-energy photon. Gamma rays are light and have no mass or charge. They are good at penetrating matter, but poor at knocking off electrons and forming ions. On to our first topic. Changes in the composition of a nucleus can result in the release of a tremendous amount of energy. Two important ways this happens is nuclear fusion and nuclear fission. Nuclear fusion is where light nuclei, those under an atomic number of 26, combine to produce a heavier nucleus. It takes 2 lighter ones to make one heavier one. Nuclear fission is the splitting of a heavier nucleus, those over atomic number 26, into lighter nuclei. 1 becomes 2. Since fission and fusion are similar sounding, it can be difficult to distinguish between the two. One helpful trick is to remember that the word fuse means bring together, and by extension, fusion is bringing smaller nuclei together. We will look at both fission and fusion in some greater detail, starting with nuclear fusion. The conditions for fusion to occur are not present on the surface of the Earth, but fusion is still the source of all life on the planet. That is because the sun is powered by fusion reactions. Partly this is due to the composition of the sun, partly this is due to the great gravity present in the sun. There is a tremendous heat and pressure at the core of the sun. There's enough heat and pressure to fuse the nuclei of the smaller hydrogen isotopes, deuterium and tritium, into a helium nucleus. This is just one of the fusion reactions in the sun, but when the helium nucleus is formed, huge amounts of energy are released. While we will not discuss how, there's a small amount of mass converted into a large amount of energy, just as Einstein predicted with E equals mc squared. The sun burns through the lower atomic mass atoms before converting the higher mass atoms to even larger atoms. This can go all the way to iron. After that, there's no energy gained from combining nuclei. The sun will have run out of fuel. Perhaps in the next 20 or 30 years, scientists will be able to harness fusion as an energy source on Earth. But until then, we will have to make do with the sun, or with fission, that is the splitting of a heavier nucleus. Energy is not released when combining nuclei larger than iron. Rather, it is released in breaking those larger nuclei apart. Smaller stuff combines and releases energy. Larger stuff breaks apart and releases energy. In the previous lecture, we called the particle before the nuclear reaction the parent nucleus. In fission, the heavier nucleus is the parent. The resulting lighter nuclei are called the daughter nuclei. Fission is accompanied by the loss of mass, resulting in the release of large amounts of energy. Again, this mass loss is very, very small and is an advanced concept that is not covered in these lectures. Still, a very, very small mass, when multiplied by a very, very large number, speed of light squared, is quite energetic. Fission does occur on the surface of the Earth. One way is through radioactive decay of unstable atoms or isotopes. Most of those are naturally occurring. Radon gas, a potentially cancer-causing compound, is a decay product of uranium. Decay can also occur through the bombardment of a nucleus by other subatomic particles. This can occur naturally, or can be man-made. Yes, humans have split the atom. Considering the word atom is Greek for uncuttable, this is a major achievement. Scientists first accomplished fission in the late 1930s with the bombardment of uranium-235 with a high-energy neutron. The 235 is the mass number of this radioisotope. The resulting daughter nuclei were barium-144 and krypton-89. Also coming out of this fission reaction were 3 more high-energy neutrons. 1 high-energy neutron started the process, and 3 high-energy neutrons came out of it. Is this a balanced nuclear equation? Is the mass balanced? Are the nuclear charges balanced? Well, it's hard to tell just by looking at it. We need to actually do the math. Looking at the mass number, has the material entering the fission reaction with a mass of 235 AMU for uranium, and 1 for the bombarding neutron. The daughter nuclei have masses of 144 and 89. And the 3 neutrons bring 3 atomic mass units. It might take some calculator work, but each side will sum to 236 AMU. Looking at charge, has the 92 protons in uranium bringing a 92 positive charge, and the neutral neutron bringing no charge. Barium has 56 protons, and krypton has 36 protons. These 3 neutrons do not have charge. Both sides of the equation have a charge of 92. Yes, the equation is balanced. Staying with those 3 high-energy neutrons that are generated in the reaction, well, they can encounter another uranium-235 atom in the sample and produce another fission reaction, which can produce another 3 high-energy neutrons that can find 3 more uranium atoms, and so on and so on. One reaction creating another reaction is called a chain reaction. When the conditions are right, the fission reaction is self-sustaining. That is, the reaction does not need to keep up the external source of high-energy neutrons, as it did to get the reaction going. The reaction itself provides those neutrons. An animation of a nuclear fission chain reaction has a uranium-235 atom, just the nucleus is shown here, and a neutron. By some means, the neutron is propelled at the uranium nucleus and forces the nucleus to split into daughter nuclei. Additionally, 3 high-energy neutrons are produced. Looking at the top neutron, it can find a uranium nucleus, crash into it, and split it into daughter nuclei. The reaction will also produce 3 more high-energy neutrons. The middle neutron from the first reaction crashes into another uranium nucleus, producing daughter nuclei and 3 more high-energy neutrons. And the last neutron from the original reaction also finds a uranium nucleus with the same result. The original reaction started with 1 high-energy neutron, and after 2 rounds of reactions, as many as 9 high-energy neutrons are formed. Those, of course, can move on to round 3 of fission reactions. That's what a chain reaction looks like on paper. In reality, it is quite difficult to get the reaction to chain. One component that needs to be in place is the amount of material. There needs to be a critical mass of the large nuclei atoms, a minimum mass of fissionable material necessary to sustain a chain reaction. This process was first worked out during World War II. 2 fission atomic bombs are used in that conflict. This one was called Fat Boy, and the other one was called Little Man. The other major topic of the lecture is half-life. It deals with the time it takes for a sample of some radioactive isotope to decay. As we saw in the previous lecture, radioactive decay is a spontaneous process. Even so, saying which unstable atom or isotope in the sample will undergo decay at a particular time is unknowable. It's like not knowing which kernel will pop where and when in a bag of popcorn. But while we do not know the timeline for each kernel, it is possible to know when half the bag has popped. Half-life will be like that. Specifically, half-life is the time it takes for half the original sample to decay. T1 half is the indicator for a half-life. It is a length of time and dependent on the particular radioisotope. Another way to look at T1 half is that after one half-life, there is one half of the original sample left. The amount of the original sample is given the symbol A sub 0, where 0 means 0 time has passed. Following along, after 2 half-lives, there will be one half of the one half, or 1/4 of the original sample left. As long as there is material left, there will be additional half-lives. Perhaps a graphical representation will add some clarity. This decay curve is plotted with the number of half-lives on the x-axis and the amount or percent of remaining radioisotope from some initial sample plotted on the y-axis. At time 0, no half-lives have passed. 100% of the isotope is present. In the popcorn example, 100% of the kernels are unpopped. That 100% is called the A sub 0 amount, the amount of the original sample. All right. How this curve works is that coming up from the x-axis gives us how many half-lives have passed. At one half-life, according to the definition, half of the radioisotope in the original sample will have decayed. The other half has not decayed. The amount of the original sample remaining is 50%. One half of A sub 0 remains. One half-life reduces the amount by one half. When a second half-life has passed, that is an additional length of time, T1 half, half of the sample that was there at one half-life will have decayed. One half of the one half of A sub 0 from the first half-life remains. Another way to say that is 1/4 or 25% of the original amount remains. Each passing half-life cuts down 50% of the amount from the previous half-life. When the third half-life passes, one half of the 1/4 remaining isotope decays, leaving 1/8 of A sub 0. 12.5% of the original material remains. A pattern begins to form. Since each half-life cuts the remaining amount of isotope in half, we can simply keep dividing the denominator by 2 to get the fraction of remaining isotope with each additional half-life. 4 half-lives leaves one half of 1/8. One half of 1/8 is 1/16. 1/16 of the original amount of isotope remains. At 5 half-lives, it's 1/32 of the original amount. Divide 16 by 2 to get 32. And at 6 half-lives, it's 1/64. Keep dividing the denominator by 2. 1/64 is a pretty small amount, so we see that it does not take that many half-lives before most of the original isotope is gone. Returning to the 1/2, 1/4, and 1/8, multiplying 1/2 is the same thing as dividing by 2. Multiplying by 1/4 is dividing by 4. And multiplying by 1/8 is the same thing as dividing by 8. This is a cleaner form of the relationship, and it allows us to develop a useful means of obtaining the remaining amount of a given sample of radioisotope after some period of time, starting with the first half-life. To get the remaining amount of isotope at 1 half-life, take the original amount, A sub 0, and divide by 2. We can keep track of what to divide A sub 0 by after some passing time using a list of the exponent of 2 raised to the power of the number of half-lives. Watch. For 1 half-life, that is 2 raised to the power of 1, which is 2. A sub 0 divided by 2. For 2 half-lives, it is A sub 0 divided by 4. 2 raised to the power of 2 half-lives is 4. A sub 0 divided by 4. 3 half-lives has a remaining amount of isotope of A sub 0 divided by 8. 2 raised to the power of 3 is 8. 4 half-lives leaves A sub 0 divided by 16. 2 raised to the power of 4 is 16. 2 raised to the power of 5 half-lives is 32. A sub 0 divided by 32. And 6 half-lives leaves a 64th of the original material because 2 raised to the power of 6 is 64. It is all binary, and it can be summed up in a relationship. To find the remaining amount of some isotope, take the original amount, A sub 0, and divide it by 2 raised to the power of the number of half-lives that has passed. It does not need to be a whole number of half-lives either. So we have a couple ways of thinking about and getting amounts of remaining isotopes based on half-lives. Can we ask the opposite question? Can we get the number of half-lives from the remaining amount of isotope? Let's try. If only 1/16 of a radioisotope remains, how many half-lives have passed? In dealing with half-lives, it's important to spot the power of 2's. The 16, or 16th, is a power of 2. How many 2's are in that value? Yeah, it's 4. The quick answer to the question is 4 half-lives. The graph can also get us there. A third way is to walk ourselves there by considering how to get to 1/16 by multiplying 1/2 values. 1/16 is equal to 1/2 times 1/2 times 1/2 times 1/2. 4 half-lives reduces the original amount by 2 raised to the power of 4 half-lives. Pick one of these ways to move from amount to half-life or half-life to amount and stick with it. If done right, they all work. It is not a big leap to bring an actual numeric amount for A sub 0. Here we ask how much of 250 grams of some starting amount is left after 3 half-lives, and after 5 half-lives. Using the equation we just developed, the way to get the remaining amount is to take the starting amount and divide by 2 raised to the number of half-lives. In the first part of the question, it asks about 3 half-lives. 2 raised to the power of 3 is 8. Take the starting amount and divide by 8. Take 250 grams and divide by 8. That gives 31.25 grams. An eighth remains. And the 5 half-lives? The starting amount divided by 2 raised to the power of 5. 2 raised to the power of 5 is 32. The starting amount divided by 32 is 7.81 grams. We will return to these two questions after discussing a few additional points. The first is a visualization of where the matter goes in a nuclear reaction. The example reaction is beta decay of iodine 131. Say at time 0, we have 100 grams of the I-131. It is a radioisotope, and after 1 half-life, half of it is gone. 50 grams remains. Where did the other 50 grams go? 50 grams of I-131 decayed into 50 grams of Xe-131. In reality, a little mass is lost, but not enough that can be measured in the school chemistry lab. After 2 half-lives, 1/2 of the remaining 50 grams of the I-131 decays into the Xe-131. Now there's only 25 grams of I-131. Graphically, the same decay curve can be used to indicate the remaining amount of I-131. In addition, the formation of the daughter nuclei, the xenon, is shown to increase at the same rate that the iodine decreases. It makes sense because matter is conserved. There is the same amount of overall matter. It just changes form. So there are 2 ways to monitor the decay of I-131. Measure the loss of I-131 or the gain of Xe-131. The other component of dealing with half-life is that not all radioisotopes decay at the same rate. The half-life of a radioisotope has to be experimentally determined. It cannot be reasoned from principles. Any particular type of radioactive isotope will have one specific half-life. That one specific half-life can be found in a range from seconds to millions of years. It has to do with how unstable the nucleus is for that particular isotope. Really unstable isotopes have short half-lives, and the more stable ones have really long half-lives. Here's a list of specific half-lives for common or important radioisotopes. Some are on the order of days, and some are much longer. Stable isotopes will be treated as if they do not decay, and therefore have an infinite half-life. Look at the half-life for uranium-235. It is the parent nuclei for some fission reactions. It has a half-life in the hundreds of millions of years. That stuff stays around forever, and is why it is so dangerous. With what we've covered so far, some specific half-life questions can be answered. For example, how many half-lives have passed after 17,100 years for carbon-14? The way to address this question is to find the ratio of time passed to the half-life of the isotope. For carbon-14, the half-life is 5,700 years. Take the time given that has passed, 17,100 years, and divide by that 5,700 years. In essence, we are asking how many 5,700 year periods are there in 17,100 years? Turns out it's 3. While the answer for this question is a whole number, it does not have to be. If the given time was 16,900 years, the answer would lie between 2 and 3. How many half-lives are there for 40.125 days for iodine-131? Same procedure. How many half-lives are there in the given time? In this case, the half-life of iodine-131 is about 8 days. Clearly, I-131 is much more unstable of an isotope than carbon-14. The ratio of time passed, 40.125 days, divided by the half-life, 8.025 days, is 5 half-lives. Again, there's no limitation that the value has to be a whole number. Now we can combine both components of half-life into a typical problem found in a textbook, keeping with the same numbers for demonstration purposes. How much of 250 grams of carbon-14 is left after 17,100 years? The problem solves in these same 2 steps. Before using that starting amount of 250 grams, we need to know how many half-lives have passed. That is found by using the time passed over the half-life equation. 17,100 years over the 5,700 year half-life. As shown before, it is 3 half-lives. With that, we can find out how much is left using the starting amount, a sub 0, divided by 2 raised to the power of the number of half-lives. 250 grams divided by 2 raised to the power of 3, 8. There is 31.25 grams of the radioisotope remaining after 3 half-lives. A similar question: how much of 250 grams of iodine-131 is left after 40.125 days? This requires a similar process. It begins by determining the number of half-lives that have passed. Dividing time passed by 8.025 day half-life has 5 half-lives. How much is left is based on starting amount, 250 grams divided by 2 raised to the power of 5, 32, is 7.81 grams. With some practice, this type of problem solves without too much difficulty. We will cover 2 more aspects of problem solving with half-life, and the first is reworking the problem we just solved. What if the question was worded as 7.81 grams of iodine-131 remains after 5 half-lives, and we want to know how much there was in the original sample, that is at time 0. Note that the remaining amount and the number of half-lives are the same as the original question, so that 250 grams will end up being our final answer. Since this question and the original question are just really opposite ways of asking about the same value, the solution is really just the opposite of that for the original equation. In that question, we use the generic equation of original amount, a sub 0, being divided by 2 raised to the power of the number of half-lives, being equal to the remaining amount. We can use the same equation if we solve it for our unknown, a sub 0. The algebra is to multiply both sides by the denominator, 2 raised to the number of half-lives, canceling out the power of 2 on the left-hand side, leaves an equation solved for a sub 0, It's not a necessary step, but if we switch sides around the equal sign, we have an equation ready to answer our question. Take the remaining amount and multiply it by the 2's. That's done by starting with 7.81 grams and multiplying it by 2 5 times. Or 2 raised to the power of 5. They are the same thing. 2 raised to the power of 5 is 5 multiples of 2. The answer is the 250 grams as seen in the original problem. Okay, let's spread this same problem out a little further. Instead of saying the 7.81 grams remain after 5 half-lives, the question asks after 40.125 days. That value is also part of the original question. The answer will again be 250 grams. But there is an extra step in the solution. The number of half-lives needs to be determined from the time passed and the half-life of iodine-131. As we saw before, that's 5 half-lives. Now the problem solves in the same way as the previous problem. Remaining amount times 2 raised to the power of the number of half-lives. And that is equal to 250 grams. There are really only a few types of questions that can be asked with this material. But some of those questions have 2 parts. Practice is what is needed. The final element of solving half-life problems is an advanced concept. It is 2 raised to the power of a decimal. Not all students will be asked to make this type of calculation. But it involves no new ideas, so it might be worth the watch. Earlier we calculated 3 half-lives passing for carbon-14 in 17,100 years. What if the time passed is 19,665 years? With carbon having a half-life of 5,700 years, time passed divided by half-life will be a decimal, 3.45. The math is straightforward, but what if the time passed is put into a question that uses how many half-lives have passed? Up until now, half-life values have been whole numbers. Does having a decimal really alter how we solve this problem? Not really. We still use the same equation, a sub 0 divided by 2 raised to the number of half-lives. Of course, 2 raised to the power of 3.45 is not as easy to handle. This advanced section is a walkthrough on doing the decimal math on a calculator. Open a calculator. Start by entering the base, the 2. Most calculators have an x raised to the y button. For us, that is 2 raised to the number of half-lives. 2 has been entered, so select the XY button, then enter 3.45 for the half-lives, and then equal. 2 raised to 3.45 is about 10.9. The x raised to the y button can be used with decimals and whole numbers. It is a useful one to know. Returning to the problem, the original amount divided by 2 raised to the number of half-lives passed is 250 grams divided by the 10.9 from the calculator. That comes to 22.9 grams. The final topic of the lecture is a closer look at carbon-14. It is essentially a half-life topic. All carbon atoms have 6 protons. The atomic number of carbon is 6. That goes for carbon-12 and carbon-14. They both have 6 protons. As we know, isotopes differ in their number of neutrons. Carbon-12 has a mass number of 12. If it has 6 protons, it will need to have 6 neutrons to get to a mass of 12. Carbon-14 needs a mass of 8 neutrons to add to its 6 protons in order to have a mass number of 14. Carbon-12 is a stable isotope. It is not radioactive. It does not decay. Carbon-14 does. Carbon-14 is a naturally occurring isotope that is formed by the bombardment of nitrogen gas in the outer atmosphere by cosmic rays. It can be formed in other ways, but this equation shows us that it is the product of a nuclear reaction with nitrogen, and that a steady supply is being made, since there is always nitrogen in the atmosphere, and we are always being bombarded by cosmic rays. How does this carbon-14 radioisotope decay? It is a beta decay back into nitrogen. Is this decay equation balanced? Atomic mass looks balanced. Charge is balanced if we remember that with an electron we're adding a -1 charge. So yes, it is balanced. The decay has a half-life of 5,730 years. Carbon-14 finds its way into living organisms. Plants incorporate it when taking in carbon dioxide from the air. Animals incorporate it by eating those plants. As long as the organism is alive, it is bringing in carbon-14. However, when an organism dies, it no longer takes in carbon, not carbon-12, not carbon-14. Starting at the time of death, times 0, the amount of carbon-14 begins to drop. Being a radioisotope, it undergoes nuclear decay. Without a new source of carbon, the amount of carbon-14 in the dead organism will follow the typical decay pattern. Since decay is constant, and the amount of carbon-14 in the air is constant, although there's some debate about that, the age of a fossil can be determined from its carbon-14, carbon-12 ratio. A visual of this can be helpful. Consider these blocks as representing the proportions of carbon-12 and carbon-14 at the time of death of some organism. No new carbon is added to the remains. For demonstration purposes, the carbon-14 proportion that is shown here is much larger than that found in nature. So what happens to the proportion after one half-life? The amount of carbon-12 is unchanged. It is a stable isotope. The amount of carbon-14 is half of what it was at the time of death. Half of the carbon-14 underwent beta decay to form nitrogen. Being a gas, the nitrogen escapes the remains of the organism. The C14-C12 ratio got larger because one of the isotopes decayed. After 2 half-lives, about 10,600 years, the carbon-12 is still unchanged, but the amount of carbon-14 drops in half again. The C14-C12 ratio continues to grow. Eventually there will only be C12. And yes, the decay produces more nitrogen. When a sample of a fossil is analyzed, the carbon-14, carbon-12 ratio gives an approximate number of half-lives that has passed and can be used to estimate the age of death. There is a limit to this type of analysis, though. After about 9 or 10 half-lives, about 50,000 years, there will be virtually no detectable carbon-14. That means there is no detectable ratio and no way to gauge the age. On the other side of the time scale are fossils that are not very old. If not enough time has passed for a measurable amount of carbon-14 to have decayed, then there's not enough difference in the ratio to deduce a time of death. The lecture winds up with a little quiz, 2 questions, to test our understanding of half-life material in this lecture. Number 1. If you have 100 grams of a radioactive isotope with a half-life of 50 days, how much of the isotope is left after 300 days? Getting amount remaining uses the starting amount divided by 2 raised to the number of half-lives ratio. We have the starting amount, 100 grams. So we just need the number of half-lives that have passed. What equation did we use to get that? Right, time passed divided by the half-life of the isotope. Do we know the half-life? Yes, it's 50 days. 300 days have passed divided by that 50 days, and we have 6 half-lives. 300 days is 6 half-lives for an isotope with a half-life of 50 days. Now to find the remaining amount, take the starting amount and divide by 2 raised to those 6 half-lives. 100 grams divided by 64. 2 raised to the power of 6 is 64. The math comes to 1.56 grams. This is a 2-step process. The second question says that potassium-40, with a half-life of 1.28 billion years, is used to date rocks. If a rock containing 7.81 grams of potassium-40 is dated as 2.56 billion years, how much was there in the original source? This problem is really just the reverse of the previous problem. Here we are given remaining amount and asked for original amount. And in the first problem, we were given original amount and asked for remaining amount. Not surprisingly, the same equation is used to solve the question. However, this equation is not solved for the unknown. Early in the lecture, a sub 0 was solved for by multiplying both sides of the equation by 2 raised to the power of half-lives. It's solved to this equation. Given is the amount remaining. What still needs to be found to use this equation is the number of half-lives that have passed. That involves the time passed divided by the half-life of the isotope. 2.56 billion years have passed for an isotope that has a half-life of 1.28 billion years. A mere 2 half-lives have passed for this ancient isotope. Now we take the remaining amount, 7.81 grams, and multiply it by 2 raised to those 2 half-lives for an original amount of 31.2 grams. Another 2-part solution. And that concludes the material of the lecture. Recapping the lecture, nuclear fusion occurs when light or small nuclei combine to produce a heavier nucleus. Most prominently, the sun is powered by fusion. While there are many nuclear reactions going on in the sun, the fusing of hydrogen nuclei into a helium nucleus is a main reaction. The forming of a helium nucleus releases a huge amount of energy. There's a small loss of matter in the reaction, and from Einstein's equation, we see that produces a lot of energy. The other energy-producing reaction we looked at was nuclear fission, the splitting of a heavier nucleus into lighter nuclei. This reaction was first accomplished by mankind in the late 1930s with the bombardment of uranium-235 with a high-energy neutron. In addition to generating daughter nuclei, there's the generation of 3 new high-energy neutrons. If those neutrons go on to bombard additional uranium-235 atoms, a chain reaction might occur. This is a self-sustaining fission reaction, and there needs to be a critical mass or a minimum mass of fissionable material in order to sustain a chain reaction. The other major topic of the lecture was half-life, or T1/2. It is the time it takes for 1/2 of the original sample to decay. That is, after one half-life, there is 1/2 of the original sample, A sub 0 left. And after 2 half-lives, there will be 1/2 of that 1/2, or 1/4 of the original sample left. To find the remaining amount of isotope, take the starting amount and divide by 2 raised to the number of half-lives. The 2 raised to a power can be solved as an exponential, or the number of 2's can be multiplied together in the denominator. The half-life of a radioisotope has to be experimentally determined and is given in a table. The range of half-lives goes from seconds for really unstable radioisotopes to millions of years for very stable isotopes. To determine how many half-lives have passed, take the ratio of time passed to half-life of the isotope. Sometimes that is a whole number, and sometimes it is not. Carbon-14 is a naturally occurring isotope that is formed by the bombardment of nitrogen gas in the upper atmosphere by cosmic rays. Carbon-14 is radioactive and decays by beta decay back into nitrogen-14. Since living creatures stop taking in carbon at the time of death, the age of a fossil can be determined from its carbon-14 to carbon-12 ratio. And that completes the lecture. Half-lives are understood to the power of 2.